And we saw the parameters corresponding to the various energy densities. Omega radiation is constrained by the CMB temperature. Right? Then there was omega baryons, for which the early constraints came from Big Bang nucleosynthesis, but then later constraints have come from CMB anisotropies. There's omega dark matter, for which there was evidence right from the 1930s using Birrell theorem on clusters, and then the 70s from rotation curves of galaxies. But then I argued that the tightest constraints actually come from, again, the CMB. And then dark energy or cosmological constant, which I argued using type 1a supernovae in the 90s, is established that the current acceleration of the universe is positive, that the universe is accelerating, not decelerating, and that it requires something beyond just matter and radiation. So cosmological constant is a good candidate. And now I also told you that today, because the CMB anisotropies are measured extremely accurately, you can infer that there must be something beyond matter and radiation just by looking at the CMB itself. You don't need type 1 explanation. So one thing that I didn't talk about was spatial curvature. So this is also interesting. So what happens with spatial curvature is that imagine the surface of a sphere versus Euclidean space. Right? So the presence of spatial curvature will change angles, because you know that on a sphere, if I start at the equator, I take two parallel lines and then I just send them off and I stay on the sphere, they will not remain parallel. They will intersect at the North Pole. Right? So this same behavior continues in higher dimensions also. So now we are talking about three-dimensional space. See, in the case of a sphere, what you're actually saying is that that space is two-dimensional. Okay, and then that space is curved, intrinsically curved. So now you have to imagine what happens in three dimensions. Okay, although you cannot picturize it, but mathematically it is exactly the same. So in three dimensions also, the equivalent of spatially flat two dimensions is spatially flat three dimensions, like in this loop. Okay, so a piece of paper can be associated with this three-dimensional volume of book. But now the piece of paper, instead of that, if I take a surface of a ball, that is my two-dimensional curved space. There is a mathematically equivalent three-dimensional counterpart to this curved space. Okay, although we cannot imagine it, it exists. You can write down the equations governing it. And the behavior of angles, etc., in this three-dimensional curved space is similar to what will happen in two dimensions. Okay, so parallel lines will no longer remain parallel and so on. And similarly, although again it is difficult to imagine, you can also have spaces with negative curvature. So these spaces, which look like balls in two dimensions, are spaces of positive curvature. You can also have spaces of negative curvature, which look like hyperboloids. Okay, so if I take the equation governing this will not be x squared plus y squared equal to constant, which is the equation of a surface of a sphere. It will be x squared minus y squared. Okay, so these kind of spaces also exist. And now we are doing everything in three-dimensional space. So this k, constant k, which appears in the Robertson-Walker metric, it tells you about the spatial curvature of this three-dimensional space. So now, depending on whether this k is positive or negative, remember the curvature actually is like negative, or I forgot. So this k, I think, is talking about the actual curvature. So if the curvature is positive, this k is 0, and vice versa, k is negative. So anyway, the point is that for either side of this k, the behavior of angles will be different. So k equal to 0 will give you some behavior of the angles, and k less than 0 will give you, angles will tend to converge in one case and they'll tend to diverge in the other case, relative to whatever happens with k equal to 0. So now if these convergence and divergence is actually happening for our universe, you can probe it by asking what is the angular diameter distance as a function of redshift in such a universe, because that is sensitive to k. Why? Because remember that both of these expressions, they depend on this sk function. So there was this sine or sine hyperbolic depending on the sign of the value of k. Okay. So this sensitivity is there. So now how can you use this? So you need a huge lever arm, so that for a particular kind of distance redshift relation, if I change the value of k by a small amount, the angle that I subtend it should change by a measurable amount, right? Because I will have, what am I observing? I'm observing the angles. So we're talking about standard rods now. So I'm measuring the angle of this, that this standard rod subtends at my eye. And I want to see what the angle would be in a universe which has a 0K or a positive K or a negative, where the rod size has not changed. See, the rod size is given by physics. It's a standard rod. And then the value of K is only changing what is the angle subtended at me, because it is changing the angular diameter distance. Okay? So now suppose my rod is placed at a close distance to me. This rod will subtend a large angle. Okay, but as I take this distance further and further, this angle will become smaller. So now, given a particular measurement apparatus, I will have some error that I incur in measuring the angle. So if the error incurred is of the size of the angle itself, then I can't do much, because then I cannot tell differences. So what I want is a situation where the rod subtends an angle such that the error on that angle is very, very small. Okay, so these are the constraints that I have in order to use this as a probe. So the cosmic microwave background offers such a rod. As I told you that the cosmic microwave background corresponds to a time in the universe when you are transitioning from the photon baryon fluid to something that is not a fluid, where photons are free streaming. So the sound horizon from the time when the fluid existed is a scale that was imprinted in the CMB. We saw it also visually, where we saw that certain patches were of some size and other patches were of other size. So you can study this scale by looking at the statistics of these hot and cold spots in the CMB. So what is called the 2-point correlation function, which I will discuss later in this talk itself. But here is one way of measuring these statistics, where what you have to realize is that on the x-axis here, don't worry about what is plotted on the y-axis. Imagine that what is plotted on the y-axis is a measure of how strong the correlations are on a particular length scale. So what I mean by correlations is, if I take one point here and another point here and ask what is the temperature here and what is the temperature here? If the temperatures are very correlated, then what does it mean? It means that if I tell you the value of the temperature at this point, you can with high probability predict the value of the temperature at the other point. That's a tight correlation. Suppose they are uncorrelated, then even if I know exactly the value of temperature at this point, I cannot say anything about the value of temperature at this point. It's uncorrelated. Okay? So now I can play this game. I take one point and I take another point separated by some angular scale theta. And I ask how tight are the correlations. Suppose I have some way of measuring this tightness. Okay, so I record this value. That at angular scale theta, which is, let's say, at half a degree scale, the correlation strength is something. Now I change the correlation, I change the angular scale. From half a degree, I make it 1 degree. And I repeat my question. Now with a point here and a point which is not half degree separated, but 1 degree separated, if I ask the same question, these faraway points, how tightly are their temperatures correlated? I have some way of calculating this correlation strength, I record this one. I keep doing this for a range of values of separation theta. Okay, and those separations are shown here on the x-axis. And roughly speaking, what is shown on the y-axis is the strength of these correlations. Alright? So what you can clearly see is that these correlations have a peak, okay, at a scale which is roughly 1 degree. Yeah. So what this is telling you is that observations of the CMB are giving you a measurement of the angular scale. Yeah. Now physics of the CMB will tell you what is the physical rod that you are actually looking at, because what is the size of the sound horizon. Therefore, this angular scale that you are measuring should be equal to the sound horizon at last scattering divided by the angular diameter distance from me to the time of last scattering, the surface of last scattering. Correct? Because the angle is just the size of the rod divided by the distance between us. So if I know the value of the sound horizon from physics and I measure the angle here, then I get an estimate of the angular diameter distance from me to that point. And the angular diameter distance, as we said, is sensitive to whether or not there is curvature. Okay, so in a positively curved universe, angular diameter distance will behave in one way. A negatively curved universe, it will behave in the opposite. So I will now play this game. I will say in my universe which has zero curvature, I have some expectation for what this ratio should be. Now, in a universe with negative curvature, it will turn out that this angular scale should shift towards the right. Okay, and you can work out why this must be by looking at the way the curvature affects behavior. And similarly, if my curvature is positive, the angular scale should shift to the left. So this is my theoretical expectation. Now I go to the data and I ask what is the actual angular scale in the universe. It is equal to this, and it happens to be this 1 degree here. And this 1 degree therefore gives you a constraint on how much curvature you can allow in DA. Okay, so this is the game people play, and it turns out that this constraint, because this angle, so what I said is that you need a large angular scale which you can measure with a very, very small error term. So now the fact that CMB anisotropies are measured with very, very high precision, with high resolution, it allows you to measure this scale with extremely high accuracy, okay? High precision. So that means that the constraint that you get on the value of curvature is also very, very tight. So you can see that the central value is very close to 0, and the error is also 1 part in, few parts in 10 to the 3 years. So this is why I was saying that for the purposes of discussion, you can safely assume that spatial curvature is 0. Okay, is this argument clear? Yeah.
Why should the first peak correspond to the sound?
Okay, this is physics of CMB we can discuss, but basically one can argue that scales that are larger than this are correlated because of other physics, okay, the Sachs-Wolf effect, etc. And then the first peak is the location of it is proportional to the location of the sound. Other peaks are harmonics of this, but the separations also tell you something extra. Okay, so all of these quantities, this entire shape has a lot of information about various parameters in cosmology. So, for example, the ratio of the height of the first peak to the height of the second peak tells you something about how much baryonic contribution there is, and so on and so forth. Okay, so this is a little bit more detailed than what I want to do, but one can discuss later. Okay, so okay, so this is this argument about curvature. There is one thing that I glossed over. Angular diameter distance also has the Hubble constant sitting inside it, because the dimensions of the angular diameter distance as a distance scale, as a length, come from the combination c by h naught. That is a dimensionful constant, and then everything else in that expression is dimensionless. It's a function of redshift and a function of the dimensionless parameters. So the problem here is that h naught appears in the expression for dA. So whatever I said is not strictly true, because what you can do is by adjusting the value of omega k0, I will move these peaks to the right and left, but I can compensate for that effect by changing the value of h naught. Okay, because h naught will just multiply this dA. So if I increase or decrease h naught, the value of dA will increase or decrease. And if I simply multiply dA with some number up or down, more than 1 or less than 1, it's obvious that the ratio will also correspondingly decrease or increase. Okay, so the value of h naught is very tightly degenerate with the value of curvature in this kind of argument. So this is why with W map, etc., or even with Planck, okay, so with Planck there is a note that I will say, but with W map it was not possible to break this degeneracy using only CMB data. So typically what would be done is to use h naught measurements from something like type 1a supernovae at very low redshift, very close to us, something at redshift of less than 0.05 or so. And then this argument combined with that constraint on h naught, because now h naught is fixed for you by low redshift supernovae. So then you can apply this argument and say that in this dA of z, I don't have the freedom to change h naught. I have fixed its value to 70 kilometers or whatever per second per megaparsec, and then I can play this game, and then I would find that omega k is close to 0. These were the state of the art about 15 years ago. But still, then people would argue that, maybe a negatively curved universe is allowed by the data, and it's just that your value of h naught is wrong. How do you know? So with Planck now, interesting things have happened, because as I was arguing yesterday, with the precision of Planck and the fact that polarization is also now measured very accurately, the effect of lensing of the CMB is very accurately measured also. And because lensing is self-consistently produced by the same structure, which has, in the past led to the development of the CMB itself, so the whole model has to be self-consistent. So you do not actually have this freedom of changing the value of H naught arbitrarily in the CMB. Okay, because if I change the value of H naught, okay, whatever, 50 kilometers per second per megaparsec. What will happen now is that the lensing of the CMB in a universe with H naught, which is this particular value, 50 or whatever, will be very different from the one that you observe. Okay, so the model will not self-consistently explain all of the CMB data. So the CMB data allows you to constrain not only omega curvature but also H naught together. And this is the thing I was mentioning by saying that the degeneracies get broken, and the effect of lensing is therefore very crucial in fixing this value of omega. Okay, so this is the discussion of spatial curvature. Any questions about this or about anything that we discussed yesterday? Because now I will switch gears. Okay.
Sir?
Yeah.
Sir, I want to ask, does CMB radiation is the result of superposition of redshift of starlights?
People used to wonder about this. So far, we are not able to explain this in this way. So you mean that stars at very, very early times? It's difficult to have a universe in which stars exist at the time of the CMB. Okay. So in the Big Bang framework, answer is no, it cannot happen. In other frameworks, in steady state models, for example, people try to do this using things like iron whiskers, etc. You need to thermalize, right? Because the CMB temperature, it's the temperature of a black body. That black body is a very perfect black body. So you need some thermalization mechanism. And people were exploring these things, but to date, there is no convincing argument that you can do everything and produce this kind of correlation structure in the detail that you see here. So you see now, I was telling somebody at the end of his lecture, you cannot just come and say that I have a model, it explains one observable, so my model is good, because it is as good as any other model which explains that observable. But your model should explain all observables. And now, each data point here is an observable. See, look at the errors of these data points. So if you come up with a model in which stars produce the CMB, you have to also explain these data points. These data points, forget about the curve that is going through that. The curve is a fitting function within some model. But the data points are data points. They have not used any model to be put down there. Okay, so one has to be careful about such things. And right now there is no model other than the standard model which can produce this entire detailed set of observations. Yeah. Anything else? There is something on the chart. Does the energy density of the CMB contribute to the value of K? No, because in the FLRW universe, K is a constant that is set by the initial conditions. So these are not connected to each other physically. Alright, so I will now switch gears and talk about initial conditions. Someone asked yesterday, the perturbations that we see, where do they come from? Okay, so this is one interesting question to ask. There are other interesting questions to ask in cosmology. Even before you reach that question, there are more important questions to ask in cosmology, and that is what we'll discuss here. Although the lecture is about inflation and alternative cosmologies, I will not discuss alternative cosmologies today. If you are interested, you should catch me later sometime. I am in office 2 to 4. You can drop by sometime and we can discuss alternative cosmologies. Okay, and subtitle is whence d2a by dt squared bigger than 0. So this you will see why I'm saying this. We have already come across this once when we said that supernova type 1a observations told us that at late times, that is close to us, the value of this quantity has to be positive because the observations are telling us this. There is another epoch in the universe where we need this quantity to be positive. We will see that. Okay. So I will only talk about the first part. Problems with the standard cosmological model and the role of a scalar field in the early universe. Okay, so this is a slide that was there yesterday, and it is good to, since we didn't discuss it, it is good to discuss it now. So when you do cosmology, it is interesting to theoretically ask a couple of questions. How far can we see in the universe? Okay, and how far can we throw? So if I sit here, how far can we see is the question, that if a source of light has thrown photons, then how far away could that source have been such that I see these photons today, okay, wherever I am at whatever time I am observing. So that is like somebody has thrown something to you and you have caught it. So how far can this occur? The other question is, how far can we throw? So if I shine a light and wait for some amount of time, which observers in the universe will be able to eventually catch my light? Okay, as time goes on and on and on, how far can my light go? And now we're not talking about intensity dimming as 1/r². Imagine I have a very very intense source of photons. I have one photon, okay, and that one photon I just throw out. How far will that photon? Okay? Or a material particle also. Material particle which I throw out at very very close to speed of light. How far? So these are kind of thought experiments, Einstein type thought questions, and you can ask these questions. So let's see how to answer these questions. So for the first question, how far can we see? The answer has a name. It is called the particle horizon. Okay, so it is defined as the maximum co-moving distance which can be traversed by material particles or light. Okay, light is the bounding case from t equal to 0, that is the initial time, up to t equal to t naught, which is whatever time you are sitting at and observing. Okay, so t equal to t naught is current epoch on this. And I can calculate this because I know how to do these calculations. I go to my FLRW matrix and I say, for simplicity, let's assume always omega k equal to 0. So my FLRW metric, remember, for omega k equal to 0 looks like this. Ds squared is minus dt squared. C is 1 in this, or maybe I can put back C squared dt squared, plus a squared of t times dr squared. There is no k, so there is nothing here, plus r squared d omega squared. D omega squared is the angular vector square, d theta squared plus sine squared theta. Okay. And now I will ask, remember this is homogeneous and isotropic universe. It really simplifies life immensely. Okay, because this set of coordinates has an origin, but that origin I can place wherever I want because the universe is homogeneous and isotropic. I choose it at my convenience. So now I am talking about a source and me as the observer. So I will just place me at the origin, okay, and the source is wherever the source is. And in fact, you can then prove that as light travels from the source to you, its angular coordinates in this coordinate system actually do not change. Okay, the geodesic equation tells you that d theta by whatever, d theta is 0 and d phi is also 0. So for such a source along which light is traveling, I can actually just solve this equation. 0 is minus c squared dt squared plus a squared of t dr squared. Okay, and the solution to this equation, the solution meaning from t equal to 0 to t equal to t naught, I have to ask what is the co-moving separation r. So I have to integrate this, and the answer is that. Right? Because I just take this to this side, I take a square root, I adjust the sign so that the integration is correctly done, and then I integrate. So I will take the a also on that side, so I'll get a c dt by a, and that will be dr. And then I integrate dr and I get r. Right? And then the remaining integral is c dt by a ka integral. So this is the answer for this particle horizon. It is the maximum distance to which you could. So what is the co-moving maximum distance that is traversable is this much, because this is the co-moving separation. Okay. If I now ask this question at today, so at 13.7 gigahertz for T naught, in the standard model of cosmology, so I put in my values of omega radiation, H naught, omega CDM, omega baryons, and omega lambda. Okay, all of these I plug in from the previous lecture. I get a number that is like 10 gigaparsec. 10 H inverse gigaparsec. We like to use this H inverse always so that this uncertainty in H is always accounted. Okay, but roughly 10 gigaparsec. So this is the distance, this is the maximum distance out to which we can see. And it is interesting that for all kinds of cosmologies that we want to talk about, this quantity is always finite, right? For expanding universes, etc. This thing is finite; it does not grow. For contracting universes, it may be interesting what happens when A of t goes into a contracting phase, but that is a separate. Okay, so for our things, it is fine. The second question, how far can we throw? This is less relevant for us, but we'll discuss it anyway. This is called the event horizon. It also comes up when you study black holes. Because what you say is that I, as an observer, am throwing signals. Who can see these signals at very, very late times? For black holes, it's interesting because there are surfaces in the universe where if the matter density is very high, then there will be these surfaces such that if an observer is sitting inside that surface and throws out a signal, that signal will never exit that surface. Okay, so that surface becomes an event horizon for that observer. Event horizon as in events beyond that surface are in X. Okay, so in technical terms, this is defined as the maximum co-moving distance to which signals can be sent in the future from wherever you are sitting. And now this is also a very similar calculation. Here, we wanted to catch signals from very early times and get them today. So we integrated from 0 to t0. Here we are sending signals from t0 and asking them to reach infinite time. Right? So we integrate from t0 to infinity. Right? So it's just this. Otherwise, it's exactly the same calculation because light is traveling on these null geodesics. So now this I can rewrite. Okay, here I rewrote it in terms of I just change variables. Okay, this is another trick that one can always use in cosmology because there is this relation between the scale factor and redshift. Scale factor is 1 plus redshift is 1 over the scale factor. Okay, and scale factor today is set equal to 1. So this is a relation that you can easily derive. And then I can use whatever time variable I want because I have t, which is my cosmic time that appears in the metric. But then I have a, which is only a function of t, and in fact, in an expanding universe, it's a monotonic function of t. So any monotonic function of time can itself be used as a time variable, right? So instead of t, I can use t squared as a time variable. You know, as t increases, t squared also increases. It increases at a different rate, but that's fine. I can live. So here I can use a as a time variable. So I can say this dt by a is actually dt by dA, right? So it will become CdA by AA dot, something like that. Yeah. But now A is 1 over 1 plus Z. And therefore it is a monotonic function of Z. Right? So as Z increases, A decreases and vice versa. So I can transform from A to Z also. I just do the chain rule again. Okay, so you can easily check that when I go A to Z, it's a nice looking integral, 0 to infinity of C by H. So it has dimensions of length, because C by H is dimensions of length, and then I'm integrating the time dependence in H of Z. H of Z comes from the Friedmann equation. Good. Now here I have to again do this. So in this case, I have kept things as a function of A, and now it becomes from A equal to 1, that is today, to A equal to infinity, which is in the future. I'm assuming that A equal to infinity is reached, that the universe is always expanding. Okay, that it does not contract. Good. So now this is the value of the event horizon. This quantity is finite in cosmologies which have a positive cosmological constant. So let's think about this for a second. Suppose, let's believe that this is true and check that this is true. So let's take a cosmological constant which is 0. I only have matter and radiation in the universe. Okay, that means that this quantity will be infinite. Does that make sense? Is it sensible that this quantity is infinite in a universe which has only matter and radiation? No? What is the question we are asking? At infinite time, so if I take a signal that starts today and I wait for infinite amount of time, how far will that signal reach? So suppose we live in a Euclidean universe, a Minkowski universe, right? There is no gravity or anything. I am a special relativistic observer. I sit at a point and I switch on a light source and I wait for infinite amount of time. How far will the light reach from me? It will reach infinitely, no? So the answer to this question in a Minkowski universe is infinite. Okay. So in a standard universe which has only matter and radiation, or actually infinite, meaning that in a universe which has only ordinary stuff hanging around, if I switch on a light and I wait for infinite time, that universe looks very much, at least in this regard, like a normal universe that we can think of. So actually, the fact that it is infinite, this quantity, will see a finite event horizon. I just mentioned an observer sitting inside a black hole sees a finite event horizon at the Schwarzschild radius of the Schwarzschild black hole. Okay, so this situation is actually similar to that. So it's very interesting because it is as if you are sitting inside a black hole. It is not really a black hole. It's a normal, well-behaved universe, but because there is a cosmological constant, the nature of light propagation changes in such a way that you cannot reach infinite distances by sending light signals. Even in infinite time, you will reach a finite distance. And it's simply because the positive cosmological constant stretches out the expansion of the universe dramatically at late time. It leads to an exponential expansion. And this is very interesting. It will come back in the next slide. Okay, good. So these are two interesting things. For completeness, let us also discuss this quantity. It's called the Hubble radius, which is just the integrand here. It is c by h. Okay, and this is a quantity which depends on time because h, remember, comes from the Friedmann equation. The Friedmann equation has an h which depends on time. Omega m by e cube, omega r by a4, omega lambda. Okay. So you can ask what is the value of the Hubble radius at any given epoch. And there will be some answer for this question depending on your whatever distribution of energy. This is not a horizon. Horizon is defined by these questions. Okay, how far? So what is the maximum distance at which something happens? This is not a horizon in that sense. It is just a length scale in the problem. Sometimes it is loosely referred to as a Hubble horizon. You will read papers in which it is called a Hubble horizon. You should take them with a pinch of salt. This is not a horizon. What it is actually telling you, you can think of in a couple of different ways. So one is, if I forget about the factor c, then this h inverse is a time, because h is a dot by h, so 1 over h is a time, right? And if you have ever come across these kind of logarithmic derivatives before, what this h inverse is giving you is the current doubling time of the universe. Meaning, if I have a scale factor which is a1 at time t1, how long should I wait before the scale factor becomes a2, which is 2 times a1? Okay, I can ask this question, and crudely speaking, I can do this calculation. So I want a2 to be equal to 2 times a1. So delta a is equal to a2 minus a1, which is equal to 2 times a1 minus a1, which is a1. So delta a by a is just a1 by a1, which is 1. Okay. So I want this condition to be satisfied, roughly speaking. And my h is just, so h inverse is delta t divided by delta a. Okay. And delta t divided by delta a, if I plug in these expressions, then this will just be delta t divided by a here. And if I'm doing this at current time, it will just be equal to delta. Okay. If a is equal to. So what this is saying is that at the current epoch, where a is equal to 1, the amount of time that it will take to go to 2 times the current epoch value is approximately given by h inverse. Yeah, it's a very crude calculation. Obviously, you should be more careful than this. But this is we are giving a feeling of what it is. This is one interesting interpretation of h inverse. Another thing that happens, which we may discuss soon, is that so actually yes, we will discuss probably today itself. And when you look at perturbation theory, which means the theory of going beyond just the FLRW metric and saying that the universe actually has small density fluctuations in the cosmic microwave background, for example, and that these density fluctuations must be dynamical, they should change with time. And what is the theory of their change with time? That's perturbation theory. In such a theory, this Hubble radius, it actually decides which wavelength perturbations will grow or not grow. Okay, so the idea here is that in the initial conditions, I can have perturbations that are excited to different wavelengths. So I have a fluctuation which has a long wavelength, which means that it's high density here, low density here. Or I have a fluctuation which has short wavelength. There's high density, low density, high density, low density. Okay, and these different kinds of perturbations can be excited by some mechanism. And then you can ask the question, this long wavelength perturbation, will its amplitude increase with time or not? It is generated with some initial amplitude, and the theory should tell you how its amplitude will change as a function of time. Same question you can ask for the short wavelength perturbation. Okay. So now the short wavelength perturbations, typically what will happen is that there are density fluctuations very close to each other. So that's like saying I have a lot of mass here, and then very quickly I have another lot of mass. So these two masses are very, very close to each other. And if you think about general relativity as a theory of gravity, you know that at very short separations, general relativity reduces to Newtonian gravity. So if my separations between these density peaks are very, very small, then I can basically think of these peaks as behaving under Newtonian gravity. So I know that if I have a mass concentration here and a mass concentration here, they will start probably orbiting each other or something will happen, right? Kepler problem will kick in or something will happen. So eventually these mass concentrations may attract each other to the extent that they become, instead of two, they become one mass concentration. So the overall density here has become larger because I have compressed a lot of mass in a small one. So if I now think about the amplitude of the fluctuations at the short wavelengths, I can expect that if the fluctuation wavelength is very small, then these amplitudes will increase. Good. So short wavelength fluctuations should increase. Now think about the long wavelength fluctuations. I have a density enhancement here, and then the next density enhancement happens here. Okay, very far away. Suppose this distance is so large that over the age of the universe, light cannot travel from here to here. Then whatever happens to this density fluctuation cannot really affect what happens here. Okay, so even if I set up this thing as the initial condition, then the dynamics here may be slightly different from the dynamics here, okay, depending on what else is happening in those. So this kind of argument tells you that there is a causal limit to how quickly the amplitude of this fluctuation can grow. Okay, so maybe this fluctuation cannot really grow at early times simply because light even has not had enough time to cross from one peak of the fluctuation to the other. So there are these two extremes now. At very short wavelengths, I can expect due to Newtonian arguments that the amplitude of fluctuation should grow. At very long wavelengths, due to causality, I can expect that amplitude of fluctuation will not grow. At least for some time it will not. What is the dividing line between what I call short and what I call long? Okay, this is the question that one has to ask. So you have to inspect the equations of the theory, which we will do. And it turns out that the answer is given by the Hubble radius. So the Hubble radius gives you this dividing line. For wavelengths that are much shorter than the Hubble radius, the amplitude of fluctuations will grow. Wavelengths that are much longer than the Hubble radius, these are called super Hubble modes or sub-Hubble modes for shorter. So the super Hubble modes, their amplitudes will remain frozen for some amount of time. Okay, and we will see how this plays. Any questions?
The existence of a finite horizon, has it got anything to do with the size of the observable?
These are two separate questions. So the observable size of the universe always has a finite value. Okay, and that is related to the particle horizon. Okay, so that is just the question, how far can we see? It is the answer to the question, how far can we see? Yeah, and the event horizon, even and what I have noted here is that this is always finite. You have cosmological constant, don't have cosmological constant, you will always see to some finite distance away from it. Because in the Big Bang, t equal to 0 is a well-defined point, and then light has had only a finite amount of time to reach. So this is always finite. It has nothing to do with whether or not the event horizon is finite. Okay. You can find relations between the actual value of the particle horizon and event horizon in specific cosmologies. So in a cosmology with a cosmological constant, event horizon will be something, particle horizon will be something else, and these two will be related to each other. Then when you send the value of the cosmological constant to 0, this one will have a finite limit, this one will have an infinite. Okay, so you can study these things if you're interested. Good. Yes.
These wavelength modes, they will also experience the redshift units expansion.
Sure. Yes.
So the super Hubble wavelength modes,
Yeah.
at some point of time earlier in history.
Excellent question. We will discuss this. So this will become clear at some point. I don't know whether it will happen in this lecture, but definitely either in this or the next lecture. This is one of the topics. Good. So let's come back to the theme of this discussion: problems with the standard model. So the first one is it's not such a big problem, but it was discussed quite a lot in the literature in the 80s. So let us discuss it here also. It's called the flatness problem. So this is a simple algebraic exercise. So just follow what I'm saying. There is not much physics here. Okay, it's purely algebra. So the total density parameter today we know is of order unity. We see the universe around us, and if I sum up all the mass components of the universe and I calculate their omega, this omega 0, which is 1 minus omega curvature, is order unity. Okay, it's the order of magnitude approximation. So in the past, if I calculate omega minus 1, which is negative of omega k, I can write it using the Friedman equation like this. Okay, this is just again simple algebra. I'm not going to derive it. It's completely trivial. Okay, I can always do this. So now I can inspect this thing and ask what happens as I send a to 0. Okay, so in the denominator, I see all these terms, a power 4, a squared, a, all of these will vanish, right? Because all of these numbers are finite. So what will remain is omega r0. And in the numerator, I have an omega k0, which is finite, and then I have an a squared. And I'm sending a to 0. So this whole thing goes to 0. Correct? Just as I send a to 0. So what we are saying is that today, this quantity is of order unity. In the past, its difference from the number 1 goes to 0. Okay? So for example, here is a particular choice of time. Okay, it is an interesting time in the history of the universe. It's a time when electrons and positrons annihilated. It is the time when neutrinos decoupled from the rest of the world. Around 1 second after the Big Bang. And around this time, if I evaluate these quantities in the standard model, for omega k0, I have not put in anything. But for all the other things, I have put in the values from the standard model. I get a number that looks like omega k0 times 10 to the minus 50. So what we are saying is that today, omega 0 is 1 plus order unity correction. It is like 0.3 maybe or something, right? Or maybe it is even a little bit larger, a little bit smaller. It is not exactly equal to 1, but it is some number close to 1. However, in the past, omega is very, 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 very close to 1. It is like at 1 second, it is close to 1 by this much amount. The difference from 1 is 10 to the minus 50. And now, what do you expect omega curvature to be? Okay, so suppose omega curvature is 0.1 today. Even then, this number is 10 to the minus 15, 10 to the minus 16. If omega curvature is 1 today, extreme case, we know it is not 1. But even if it is 1, even then, the early universe has an omega which is extremely close to 1. So this is a puzzle. Why was the early universe so finely tuned to be close to the then value of omega equal to 0? So why was it close to flat? Okay, so this is the flatness problem. It's like a fine-tuning issue. People don't like these numbers. When you say that something is close to 0 to 1 part in 10 to the 15, this is a problem. So this is but fine, you could argue that, okay, who knows why this happened? The universe is whatever it is, omega k is whatever it is, and the universe was close to being flat. Could live with it. Okay, there is another issue which happens in the same performance. So this is called the horizon problem, and this is not a problem of aesthetics. The previous one you could say is, who cares? This is the number, it is what it is. It does not affect anything. So let's live with it. This problem is a problem of fundamental physics. So let's understand this a little. So here, if you consider the co-moving particle horizon, which we just discussed, you evaluate its value in the standard model at the photon decoupling epoch, at the time when the CMB was introduced. Okay, so you know what time that is, and you know the parameters that you have picked. So let's do that. So this someone pointed out yesterday, it's a redshift of 1100. So in this cosmology, the value of the co-moving particle horizon works out to about 180 H inverse angles. You can do this. It will be plus minus 20% variations depending on what parameters you use. Good. Now, take this particle horizon and ask the question. I want to ask the question: if I take 2 points which are separated by the maximum distance that they could have been separated by, starting from the Big Bang, okay, in terms of light travel time. I take that separation, I place it at the photon decoupling epoch, and I make it subtend an angle to me. All right, I want to ask what is this angle? Okay, that is the question. So in order to do that, I have found the separation, which is my rod, which is 180 H inverse MPC. Now I need to know the angular diameter distance from that point to me, okay, from that epoch to me. So the co-moving angular diameter distance, I have to account for 1 power of the scale factor. So that's why it's dA multiplied by 1 plus z, it's dA by a. And that you can work out. It is this R source at the decoupling epoch. It is about 10 H inverse gigapascal. Okay. So now I have to take the ratio of these two. And when I do that, I get an angle which is about 1 degree. Okay, it's a simple calculation. But what is this saying? This is saying that if I take 2 points which are separated by more than 180 H inverse MPC at t equal to 0, then because the particle horizon is only 180 H inverse MPC, these 2 points are causally disconnected. They will never be able to talk to each other by sending rays of light to each other. Okay, so suppose something is 200 H inverse MPC separated, then particle horizon is only 180 H inverse MPC. So from the Big Bang up to the photon decoupling epoch, these 2 points cannot talk to each other. They cannot know about each other. Okay. So now, if I look at the CMB, and okay, so now these 2 points are whatever, and now I am at the threshold of being causally connected. I place that threshold at 180 H inverse MPC. So I take 2 points that are just on the threshold of being causally connected, and I ask what angle would those 2 points subtend at T. That angle is about 1 degree. The implication is that suppose I now consider points which are separated by more than 1 degree, let's say by 5 degrees, at the last scattering epoch. I can find such points in the sky, right? At the time of last scattering, those 2 points were causally disconnected from each other because their separation is larger than the particle horizon at that time. So the temperature of the CMB that I see from that point and from that point, there is no reason for it to be the same. Okay? There's absolutely no reason for it to be the same. The only distance scale, the length, angular scale over which I can expect a uniform temperature is about 1 degree. So I should actually see a CMB sky which is like 1 degree size patches in the sky, overlapping maybe. But the coherence of the temperature should not be at more than 1 degree scales. But in fact, if I just look at the CMB, the temperature is 2.725 Kelvin everywhere, up to these tiny fluctuations which we will discuss later. Okay, but the thing is actually completely uniform. So that there was no reason to do that, to have that. There should have been order 1 fluctuations. 2.7 in one place, 3.5 in another place, 10 point something in another place, 0 in some other, not 0, but 0.1 in some other place, So why is that the case that is not happening? Why is the CMB so uniform across the sky? If you cannot answer this question, you have a problem with causality. You see, so now it's not an aesthetics problem anymore. It's just what it is, the number is what it is. No, causality will go for a ride if you do this. You have to answer this question. So let's fix the horizon problem. People worried about this in the 80s and they came up with ways to try to fix it. So you analyze the root cause of the problem. People did it in different ways. I'm following one approach which is there in Scott Robinson's, and I don't know where. So remember that the co-moving particle horizon is given by this expression at any given epoch t. Okay, we showed it in the first slide at current epoch, and in the previous slide just now I evaluated it at the epoch of last time. So you can evaluate it at any epoch, and this is what it is. And I'll rewrite it as this integral in terms of the scale factor as a variable. Alright? So now notice what is happening here. There's a logarithmic measure, d log a, and then there is c by ah. C by h is the Hubble radius, which is a physical Hubble radius. So if I take c by h and I divide by 1 power of a, I get a co-moving Hubble radius. Okay, so I am integrating the co-moving Hubble radius with a logarithmic measure in a. That is my particle horizon. Okay, so I can think of it this way. So now this co-moving Hubble radius, if I don't have any strange creatures in my energy densities, I have only matter or radiation, then this thing always increases. Okay, as a function of, as A increases, this thing increases, which means that early A, small values of A, the value of this co-moving Hubble radius is very small. So what this is saying is that there is very little contribution to this integral at early times during radiation domination because the co-moving Hubble radius is just proportional to B. Okay. So now this is the reason why there is a problem, that I have not built up enough of a particle horizon at the last scattering. How can I solve the horizon problem? I need to make sure that points that are separated by even 180 degrees in the sky are inside each other's particle horizon at the time of last scattering. So I need to make the particle horizon at last scattering very, very large compared to any separations that I carry. So in order to do this, one possible solution is to allow for a brief phase in which you say that, okay, maybe the universe was radiation dominated at extremely early epochs, but then or something happened at extremely early epochs and things were causally disconnected because the particle horizon was very small. Now allow for a brief phase in the expansion of the universe where these causally disconnected points actually become causally connected simply because the particle horizon dramatically increases. Oh, sorry, it dramatically if the co-moving Hubble radius dramatically decreases. Okay, so if the co-moving Hubble radius dramatically decreases, so okay, let me build up the argument, it will become. So I will allow for a brief phase in which previously causally connected points become temporarily causally disconnected. So I misspoke. What I want is points that are 180 degrees separated should somehow know about each other because the temperature there is the same as the temperature. Okay. In a typical standard universe, I cannot do this because my calculation tells me that they should have been causally disconnected at the time of the photon decoupling. So I want to allow for this. Okay, so at the time of photon decoupling, it appears as if they are causally disconnected, but earlier than that, there was a phase when they were causally connected. Okay, so I want two causally connected points to go through a phase where they become causally disconnected. Then that phase ends, and then normal expansion begins after. Okay, so the temperature, the thermalization has happened during the time when they were causally connected to each other. Then I will create a phase where they become causally disconnected by decreasing the Hubble radius by a dramatic amount, and then I will allow the Hubble radius to increase again in the standard manner. So I will insert a little piece of the evolution of the universe, which is non-standard, so that this causal disconnectedness comes in. And if I forgot about this phase, then it would appear as if these points are disconnected, but actually they are connected because they went through this phase, and before that phase they had become connected. So in order to do this, what do you need? You want a phase in which the co-moving Hubble radius decreases as a function of time. So now mathematically it's very simple. I want ddt of the co-moving Hubble radius to be less than 0. So ddt of 1 over the co-moving Hubble radius has to be bigger than 0. Okay, so this A times whatever is appearing here is the inverse of this point. Okay, so my ddt of this has to be bigger than 0, and it is very straightforward to see that that is just the condition that the acceleration of the scale factor during that non-standard phase should be positive. Right? So this is the way that this problem will be solved, and now you have to invent a mechanism which does this. Okay, so this people do in different ways, and there is an argument that asks you, okay, for how long should this phase last? So that is given here. You can think about this later. But basically, you can do this calculation starting from some early epoch where I had causal connectedness. I have a brief phase in which things become causally disconnected, and then I have to end that phase and allow the standard evolution to take over from there. How much is this phase? Okay, so now I do a matching exercise by saying that I want things which are separated by the size of the observable universe today to be in this regime where they would have been causally connected early on, and that gives me my boundary condition for the problem. It turns out that 60 e-folds of increase in the scale factor. So if I think of the scale factor as exponentially increasing with a time scale which is related to the expansion rate, then how many such e-foldings should I allow for? Typically 60 e-foldings is enough. If I have more than that, I am okay, because all that will mean is that points that are separated by more than the currently observable size of the universe will also obey this connectedness property. But if I do 60 folds, I will be consistent with all current observations. Okay, so this is the way this is done. And in order to realize this, one typically invokes things like a scalar field, for which you can write down energy momentum tensor. And in a homogeneous and expanding universe, this energy momentum tensor has only a rho and a p, which are functions of time. And in terms of the scalar field itself, in terms of its time derivative and potential that you will work for the scalar field, the rho and p look like this. So now what one argues is that how can I make sure that my scale factor accelerates when this is the source of the Friedmann equation? And you can do it by making sure that this phi dot term is very, very small compared to the v of phi. Okay, v of phi is like a potential term, phi dot squared is like a kinetic term. So if I make the kinetic term very small compared to the potential term, you can see that this rho will be roughly minus p will be minus rho. P equal to minus rho we have seen before. Cosmological constant did that for me. Okay, and cosmological constant leads to accelerated expansion. We also know that. So this is what this field is doing. Okay, it is it is demanding a phase in which this field is behaving very much like a cosmological constant. But you cannot keep it to be exactly a cosmological constant, because a constant is a constant. If you put that into the initial conditions, you will never have an end to that phase, right? It will always continue to accelerate forever. Our universe will never be created. So what you want is that the space should end, and that's why you need a dynamical quantity here. It cannot be a constant, and the way it is realized is through a field like this. Okay, and this slow roll means that the potential dominates for an amount of time which is equal to about 60 volts. And then you want something to happen to this field so that this expanding, accelerating phase ends. Okay, so successful model requires this phase to end, and more than that, you want your standard model particles to somehow appear in the universe. Okay, because what will happen in a completely accelerating phase, exponentially accelerating phase, is that the universe will become extremely cold, and you will not have a CMB which has the correct temperature at the correct time. Okay, the temperature of the CMB will be driven very close to zero. So, in fact, there will be all particle species will have a density which is driven to zero exponentially. So, in a successful model, this phase should end, and somehow your standard model particle should be created. So, this people try to do. Okay, so this field is called the inflaton, and what one typically argues is that okay, at the end of inflation, this inflaton should decay and it should create standard model particles. Okay, and how it does that goes by the name of reheating. All of this is very, very uncertain in terms of being able to test what is happening. Okay, there are no real observations which will allow you to probe what happens in reheating, except for some ways which we can discuss later. But even these ways are not really very strong probes of exactly what the mechanism is. But this is one way to think about it, is that you have to do all this. Okay, because without this, you have a very serious problem in the early universe. Causality would be broken. So in order to save causality, you have to go to pretty extreme lengths to come up with ways in which the physics is still consistent. One byproduct is that this flatness problem is trivially solved. Okay, because you can check that in such a universe, omega will go to 1 exponentially in this phase of accelerating expansion. So this is no longer a problem. It was not a very serious problem to begin with, but it's a happy coincidence that you don't have to invent something else to solve it. Okay, once you create this invention, you will also solve the flatness problem. But more importantly than this, something else that is very nice happens in this model. Although this universe is homogeneous and isotropic, and it is very, very smooth because of this inflaton field, you can argue that if this inflaton field has quantum fluctuations, then these quantum fluctuations will actually become the seeds of late-time structure formation. Okay. So this is a clean prediction of these inflation models, that if I do quantum field theory in curved spaces, which is actually a very well-established set of framework. Okay, so it is much older than inflation. And people have studied the nature of quantum fields as perturbations around black hole spacetimes, for example. Hawking effect is a classic example of this kind of calculation. Okay, so you apply the same theoretical framework to this epoch and this particular model, and you will see that the model predicts that there must be some quantum fluctuations which will lead to fluctuations in the energy density and the gravitational potential of the late time units. So these are the seeds of late time structure formation, and this is then the answer to the question, where did these fluctuations come from? Say, in our current understanding, something that is like inflation must have happened, which solves the horizon problem for you and lays down quantum fluctuations which become the seeds of later structure formation. Okay. Any questions about this? Yeah.
Could you please explain more about quantum physics?
This, unfortunately, I will not have time to do just now, because in order to do that, mathematically it will take a while. But the simple answer is that what you can do is to reduce the problem of flux. So what you say is that my inflaton field is this phi. Okay, this phi is my field, and it has some fluctuation. So phi is equal to some classical quantity phi bar, which depends only on time, plus a delta phi, and that delta phi is a small fluctuation, and it depends on space and time, and it is a quantum operator. Okay, so my phi is actually a quantum operator. It has a classical part which is just phi bar, and then the quantum part is a small fluctuation. So this quantum part I can analyze using, I have to write down the equations governing, I have to write down the standard, I do standard quantum mechanics, and I realize that the equations governing the modes of this quantum operator are very closely related to the harmonic oscillator, the quantum harmonic oscillator that we usually study. Okay, so except that you have to allow for the frequency to be time dependent in a certain. So when you do that, you can systematically find solutions to the evolutions of the amplitudes of these modes, just like you would do for a standard harmonic oscillator. For a harmonic oscillator, there is only one oscillator that usually you would think about at a time. Here, there is a collection of oscillators. There is one oscillator at every location in space. So it's a field, it's a quantum field. Right? So this is quantum field theory in a curved spacetime. Usually quantum field theory is done in Minkowski spacetime, which is the way it was developed. But then people also asked, how do I translate that mathematics when my spacetime is curved? So when I have a classical curved background given, and I have a quantum field that's fluctuating on this line. So there is a well-defined approach to doing this. And when you do this, you will get predictions for the strength of the fluctuations in this quantum field. Okay, so the strength of these fluctuations means in an RMS sense, how much is the field going up and down. Okay, so that is the question that one addresses here, and there are clean predictions for this. Okay. So this is a good time actually to talk about the statistics of these fluctuations. So here, this will be useful down the line also. I will not go very far today, but tomorrow's lecture we will talk about structure formation. So this will set the stage for that discussion. So in the simplest of these inflationary models, so this whole scheme is called inflation. Okay, inflation meaning rapid expansion. Okay, so that is the name given to this mechanism. And the field itself is called the inflaton. Okay, proton, electron, inflaton. And these models are called inflationary models. What you use for this V of phi is more or less up to you. Okay. It's really undetermined. But there are constraints that come about. So you can reduce the class of models of V of phi that you want. And for a restricted class of models, you can ask some very specific questions which have some observable consequences. So we'll see one example next soon. But by and large, these models are, there is a lot of freedom. All right. So now the simplest of these models, which are called single field, meaning that I have only one phi of x and t, and that is the only field that I use to do this inflationary exercise. Okay, so single field and slow roll. Slow roll is the idea that in the comparison between the potential and the kinetic term, the potential term is more important. The kinetic term is less important. So why role? Because if I think of a particle in a potential well, in a gravitational potential well, if I place a particle at the bottom and I kick it, then it will oscillate. Okay. On the other hand, if I take a potential well which has a maximum value somewhere and I allow the particle to start from here with zero velocity, it will roll down. How quickly it will roll down will depend on how steep the potential well is. What I want here, okay, so if I have a very steep potential well, then it will roll down very quickly. Okay, so its kinetic energy, the rate of change of its position, will be very rapid. So in this comparison, think of this as the position of a particle in standard, the standard Newtonian mechanics. So if I have a very steep potential, then this phi dot term can be very large compared to the value of the potential, because it's the gradient of the potential which determines phi dot. The value of the potential may be small compared to the value of phi. So this is a fast rolling part. If I want the particle to roll slowly, I need its kinetic energy to be very low. So I need a potential which is very, very shallow. Okay. So in a shallow potential, the particle's kinetic energy can be adjusted to be very small compared to the value of the potential energy. I can keep the whole thing at an elevation and I only allow it to roll very slowly. Okay, so for this inflaton field, because I want accelerated expansion eventually in the Friedmann equations, I have to arrange a situation where this phi dot term is smaller than the v of phi term, so that p becomes approximately minus rho and I have my accelerated phase. So these are the simplest models, single field slow roll. And in these models, you can make these clean predictions that I'm talking about for the nature of the fluctuations, the quantum fluctuations. There are other models of inflation in which you can say that maybe there is a single field, but it is not always slowly rolling. Maybe for a brief phase, it had some crazy fast roll and so on. That will lead to different predictions for the nature of these quantum fluctuations. Okay. Or I can have models in which I don't have a single field, I have multiple fields. Maybe I have two fields. One of them is slowly rolling, another one is doing something crazy. Okay, and now the quantum fluctuations are determined by the fluctuations of one of the fields, not of the other. I can arrange for such things. I have a lot of freedom. Okay, and in all of these models, I will have different kinds of predictions for the nature of these fluctuations. So the fluctuations eventually will become a probe of what kind of model you are allowed to consider during the inflationary epoch. Okay, so although the inflationary epoch is talking about the background expansion, it's really the fluctuations which will hold the key to distinguishing between models. Okay, so let's focus on these simplest models, single field and slow roll. It turns out that in these models, one predicts a distribution of these fluctuations which is very close to being Gaussian. And the reason for that is because the equations governing the amplitudes of the modes of these fluctuations are very close to a harmonic oscillator with some constant mass. Okay, and a potential which is just something like m squared, x squared kind of. So a standard harmonic oscillator potential. And this mathematics actually guarantees that the statistics of your fluctuations will be very close to Gaussian distribution. Okay, so there is a calculation that one has to do, see why this happens. For the time being, just assume that this is the case. I can give you references for where you can read up. Okay, so now in such a case, what will happen is that the fluctuations of the spatial curvature of your metal. So you have to ask what is it in the whole system which is fluctuating. Okay, what are these perturbations? So you can say, okay, it's the temperature of the CMB which is fluctuating. But temperature of the CMB is really the energy density of the photons in that location. So it's the energy density of the photons which is fluctuating. But that is not really the fundamental thing either, because the energy density of the photons responds to maybe the energy density of matter around. Okay. So all of these things are coupled to each other. So there is really only one fundamental degree of freedom, which is the fluctuating degree of freedom. And that degree of freedom will tell the photons to fluctuate, it will tell the mass to fluctuate, it will tell the gravitational potential to fluctuate. Okay, so you have to reduce the problem to that one fundamental degree of freedom whose fluctuations you need to describe. There are several ways of doing this. One convenient way is what is called the curvature perturbation. Okay, so you write down the Friedman, the Robertson-Walker metric, and you allow it to have perturbations around the standard expression. So this is the standard expression. For example, if I now insert a quantity which looks like 1 plus some zeta of x and t, or r and t, and I say that this zeta is a very small number. Okay, so then this is a quantity which is describing a fluctuation around the smooth and expanding, like the homogeneous and isotropic. Okay, so one has to play these kind of games, but now you can ask, why am I only multiplying it here? Why can't I have it here? Okay, so you can have it here. So usually people will say, let's say this is some psi, and then here I will insert a 1 plus some phi, okay, of x, of r. And now I will allow both of these degrees of freedom to exist in my equations. I will write down the dynamical equations which govern these perturbations, and I will try to analyze the structure of these equations. So this is a involved procedure. I will show you in tomorrow's lecture a restricted version of this problem. Okay, but what one can do is to basically realize that at the end of the day there will be one quantity, one field whose perturbations you have to describe. That field is called the gauge invariant curvature perturbation. Okay, and the important thing for the current discussion is that these inflationary models predict that the distribution of these perturbations will be approximately Gaussian, which means that this field will be a Gaussian random field. Alright, so let's understand what it means to have a Gaussian random field. You've already seen an example of this when I showed you the image of the CMB temperature anisotropies. That was one realization of a Gaussian random field. So if I want to discuss Gaussian random fields in general, I have to talk in terms of probability distributions. So let's start with a single number. So if I have a single number and I say that this number, a variable x, is a Gaussian random number. What does it mean? That I do not know what the value of this x is, but I know a probability distribution function for the value of this x. So that if I have an experiment in which I can sample the value of this x somehow, I do some experiment and it outputs the value of x for me. My understanding that this x is distributed according to a Gaussian says that if I do this experiment many times and I histogram the values of x that I get, they will trace a curve which looks like a Gaussian shape, right? So it is not the value of x which is Gaussian, and it's not that there is an x and then I take and then the value is e to the minus something, right? It is not like that. X is a number. I sample it once, I get x1. I sample it again, I get x2. I do it 1,000 times, I get x1, x2, x3 up to x1,000. I take all of these values and I put them in little bins. I ask how many values do I have of x from minus 5 to minus 4.5, from minus 4.5 to minus 4, and so on. I create a histogram. The shape of that histogram is Gaussian. This is what it means for a number to have a distribution which is Gaussian. Good. Now I say, okay, I have a number which is the value of the temperature at this location, and another number which is the value of the temperature at a slightly different location. And I tell you that both of these numbers are Gaussian distributed. So now what does it mean? If I sample the joint distribution of these two numbers, I will always get pairs of numbers. I will get a value of temperature at the first position and a value of temperature at the second position. And my theory is telling me that these two values are drawn from a joint distribution which is a Gaussian. Both are Gaussians. So how can I write down a joint distribution which is a Gaussian? Each of them has to be individually Gaussian also, but I can also allow for correlations between them. So if I know the value of one, maybe I know the value of the other.
Hello.
There is a mathematical description which tells you what is the joint distribution of two correlated Gaussian random variables. Okay, it is a bivariate Gaussian random. I can now go ahead and ask this question for every point on my CMB map. Let's say I have 10,000 pixels on my CMB map. Each number is the temperature at that particular pixel value, and each number is Gaussian distributed, right? And each of these numbers can be correlated with all of the other numbers also. So if I have 10,000 pixels, then I am trying to describe a 10,000 by 10,000 correlated Gaussian. Okay, so this is the idea that now basically I have a map in which every point is a Gaussian random number correlated with all the other points. And I have to ask what is the joint distribution of all of these, and I can write it down. And this distribution defines a Gaussian random field. So if I now sample this random distribution once, I will get one realization, it will look like that CMB map. I sample it again, I will get a slightly different looking CMB map, and so on. Good. So this is the idea. Now, what characterizes a Gaussian random field? So it is useful to think in, so this is what this slide is about. Okay, so this slide defines mathematically what a Gaussian random field is. Yeah, so it's a definition slide. So it is not that, oh, where did this come from? Whenever I like to tell students that if I put 3 lines, you should close your eyes and close your ears and not discuss further. Because that is a definition. Okay, you cannot argue with it. It is not a derivation, it is a definition. This is a definition slide. So let's go through this quickly. So I want to describe a field, which means that there is a value of my quantity at every position x. So x tells me where I am in space, and the quantity zeta of x, think of it as the delta t over t at different locations. So x could be location in the sky or in 3D space, and zeta could be any variable that you want to think about, temperature fluctuation, density fluctuation, in this case, this temperature. So now if I consider a zeta of x, I can think in terms of a Fourier transform of this zeta. I hope everybody is familiar to some level with Fourier transform. If not, please go and look up some standard. Wikipedia will tell you what a Fourier transform is, how to do it. Okay, so I can write the zeta of x, and my notation may be slightly non-standard. Usually people will put a tilde and put brackets and put k, etc. I like to write things with a subscript k. Okay, so this zeta subscript k tells me the amplitude of the Fourier mode whose wave number is k. Okay, so remember, when I do Fourier transforms, I go from my position coordinate x to a conjugate variable which has dimensions of 1 over length. It is called wave number. So if my x is 3-dimensional, I will have x1, x2, x3. And for each of the x1, x2, x3s, I will have a corresponding wave number k1, k2, k3. Right? So this k is a 3-dimensional vector if x is a 3-dimensional vector. And k dot x is a quantity which is dimensionless. So if x has dimensions of length, k has dimensions of inverse. Okay? And the Fourier transform is constructed by saying that I will write any function. So I have some function which looks like this. I will write it as the sum of sine waves. Okay, so I will have some sine waves like this, I will have some sine waves like that, I will have some sine waves which are fluctuating very rapidly. And I will ask each of these sine waves, I want to add them up with different coefficients. Okay, so I will take a1 times the first sine wave, a2 times the second sine wave, a3 times the third sine wave. I will keep adding them up. What are the a1, a2, a3s that I need such that the sum of all of these weighted sine waves will look like this function? Okay. So that collection of a1, a2, a3s that I get is the Fourier transform of this function. Okay. So that is the way I have written it. And here, instead of writing it as a summation, I have written it as an index. That is all I have done. Okay, so it's just a summation over sine waves. Instead of writing sine waves, I have written e raised to ikx, which is whatever, cosine of something plus I times sine of something. So I have a bunch of complex sine waves here. I have summed over them, and I have put in these coefficients, which are the equivalents of what I was calling a1, a2, a3. Okay, and the coefficients are labeled by what? By the wavelengths or wave numbers of those sine waves. So a1 was the coefficient of the longest sine wave. a2 is the coefficient of the intermediate sine wave. a3 is the coefficient of the shortest sine wave. Okay, so that 1, 2, 3 is telling me something about the wavelength of the sine waves. Same thing here. This k is telling me something about the wavelength of the sine wave. It's just an index. Good. So now this zeta of k, because I am multiplying with a complex quantity here, and I want a real quantity outside, zeta k itself has to be a complex quantity. Otherwise, I will not get a real quantity. Okay, I have to make sure that this combination gives me a real quantity. Okay, so zeta k has to be complex in general. So I can always write it as ak plus ik, right? Where ak and bk are real numbers, and I keep this label k always to tell me which k I'm talking about. Or I can also think of it as some capital AK times e to the I phi k, which is again capital AK and phi k are real numbers. But now AK and BK would be real numbers going from minus infinity to infinity. Here, capital AK is a number going from 0 to infinity because it's an amplitude, and phi k has to be periodic. It can only go from 0 to 2 pi. Okay, or some range which has a length of 2 pi. So I can characterize this zeta k, which is a complex number, in either of these. I have to also ensure, as I said, that this quantity is real. Okay, so I have to make sure that when I go from k to minus k, this real part remains the same, and the complex part picks up a minus. The imaginary part picks up a minus. Okay, and you can see why that is, because when I go from k to minus k, I will have e to the minus ik. Right, so from e to the plus ik, if I go to e to the minus ik, I have taken a complex conjugate. So that is what I need to make sure here also. When I go from zeta k to zeta minus k, I should get the complex conjugate. Because then when I do the summation, I will get something which is the quantity plus its complex conjugate. And the sum of a complex number and its complex conjugate is the real part of that complex. 2 times. Okay, so I will guarantee that I get a real quantity by making sure that this condition is true. Okay, so this is just a reality condition. Similar condition holds for the amplitude and the phases. Okay, and therefore the zeta minus k is the complex conjugate of zeta k, and that means that zeta of x is real. You can check this. Okay, this is all just manipulating a Fourier transform. Where is the Gaussian random field? This is where it comes. When I write down this zeta k, if I want zeta of x to be a Gaussian random field, the AK and BK that I have here, they should be, so remember, what are AKs and BKs? Each, for every fixed K, AK is one number and BK is one number. So now what I am saying is that for each K, these AKs and BKs should be Gaussian random numbers for each K. Okay? What kind of Gaussian random numbers? They should be their distribution should be a Gaussian whose, for a Gaussian, remember, what are the two quantities that I need to describe a Gaussian? Mean and variance, or mean and standard deviation. Okay? So mean and variance I have to define. That completely fixes my Gaussian distribution for me. So I am saying now that these two numbers have to be Gaussian distributed with a mean which is 0 and a variance which is some function of the magnitude of k. So I am calling that function p zeta of k. Okay? And I am doing this for a reason which will become clear just now. It is for later convenience, I am calling that function in this way with a factor 2 and so on. Okay, so just it is some function of, it has to be some function of k. It in general could be a function of the vector k, right? Because this k is a three-dimensional vector. So in general, you could say, okay, I want a function which depends on the full vector k, depends on the magnitude and the direction of that vector. But I am saying that it should only be a function of the magnitude of k. We will see why that is. Okay, but for the time being, just keep this in mind. An important part here is that for each k, these AKs and BKs should be distributed like this independently of each other. Okay, so the BK should not know what AK is doing, AK should not know what BK is doing. They are independent Gaussians. Not only that, when I change the vector k, I go from k1 to some k2, then I had AK1 and BK1 here and AK2 and BK2 there. AK1 and BK1, they are independent of each other and they are also independent of AK2 and BK2. And of course, AK2 and BK2 are also independent of each other. So this is very nice because all you are saying is that for every k, I have to draw two independent Gaussian random numbers. Then I go to the next k, I draw two more independent Gaussian random numbers. I keep doing it for all the k's that I can. Okay, and I will get a bunch of independent Gaussian random numbers. I take their values, I plug them into this expression zeta k, okay, and I construct ak plus ibk, and then I plug that set of zeta k values into a Fourier transform expression, and I get zeta of x for any x that I can. Okay, so that is how I construct a Gaussian random field realization. And this is the way it is done. Okay, and similarly, if I want to talk about the amplitude and the phase, then the AK should be exponentially distributed and the phase should be uniformly distributed. Okay, or you can show that is equivalent to having the little AK and BKs being Gaussian distributed.
So this is cleaner to understand why a Gaussian distribution appears. This is less clean, but it is mathematically equivalent, and in some cases, it is also more convenient. Okay. So now, what is this function p zeta of k? This is the function which defines for you the variance of these fluctuations at every k, right? Because that is the way it is appearing. So I can write it in the following way. If I take zeta k and I take zeta conjugate at some k prime, k and k prime are different, and I take an expectation value. So I take a product of these two numbers and I take an expectation value. This is like calculating the two-point function of a Gaussian variable, the square of a Gaussian variable, and I take its expectation value, right? X squared average people will calculate. So this is like taking the variance. It's not really a variance, it is a cross correlation. Because I'm taking one k and I'm correlating it with the second k prime. So what this is saying is that if I do all of this independently, I will get an expectation value here, which is proportional to a Dirac delta in k minus k prime. Okay, because when k is not equal to k prime, I should have no correlation between the numbers at k and the numbers at k prime. This will ensure that. And this p zeta is defined in this distribution language in such a way that this expectation value contains a Dirac delta. Okay, and there's a Dirac delta simply because we are talking about continuum Fourier transforms. Okay, because you know that integral d3k of just e power I k dot x without any zeta k or zeta k all equal to 1, that integral is not defined, right? So it has to be defined in the sense of a distribution, and that distribution is the Dirac delta. Okay? So it's Dirac delta of x is equal to integral d3k e power I k dot x. So it's not surprising that Dirac deltas appear. And here also in the expectation value of Dirac delta appears, all it is telling you is that different k's are not correlated to each other. But when k is equal to k prime, I need to have some description of the variance there. And this p zeta of k is telling me that distance, that variance. Why is only magnitude of k appearing? Okay, so we'll just discuss that and then I will stop. This Dirac delta is telling you that there is statistical homogeneity in the system. Okay, so the way to see that is that if instead of zeta k prime, I took zeta x and zeta x prime, and then I take expectation value. Okay, so if I calculate the expectation value of zeta of x times zeta of x prime, and for zeta of x and zeta of x prime, I plug in these expressions. I have to be careful that zeta of x has one integral over a k. Then when I multiply by zeta of x prime, I should not again integrate over k. I should integrate over a k prime. I have a different summation. Okay, so it's like integral d3k prime. Then I will have e power I k dot x, zeta k. Then I will have e power I k prime dot x prime, zeta k prime. Okay. Then I manipulate things to bring the expression into a form which has two integrals, d3k prime, 2 pi cubes, etc. And an expectation value of zeta k prime zeta. Okay, or I can also keep it in terms of zeta k prime. When I do that and I plug this thing in, I will get some prediction for this object. What you will find is that this is some function only of x minus x prime. Okay, if this p zeta of k depends on the magnitude of k also, then in general I will have a function which depends on the vector x minus x prime. The reason this x minus x prime is appearing and not x and x prime separately is because of this Dirac. Okay, this you have to do the calculation, please do it yourself and check that this actually happens. If this Dirac delta is here, then this quantity is a function only of x minus x prime. So what is this saying? It means that the value of zeta at a particular x doesn't really matter. It does not matter where you are sitting in order to do this two-point quantity. What matters is the separation to the other point. In a two-point quantity, you have 2 points. So it's only the separation between those 2 points that is relevant for this calculation. The location where you place them does not matter. So if I take a rod which is this chalk pointing in that direction and I place it here, or I place it at the end of that loop but pointing in the same direction, it doesn't matter. Okay. The only thing that matters is what is the separation vector between these 2 points. So that's what this is saying. This is the idea of statistical homogeneity, that calculations of statistics like the variances don't care about where you are sitting, They only care about separations between the endpoints that you are calculating the statistics of. Okay, so this realizes statistical homogeneity. Now, if I additionally say that p zeta of k does not depend on the vector k, but only depends on the magnitude of k, and I repeat my calculation, what you will find is that this object becomes a function only of the magnitude of the separation between these 2 points. So this is directly connected to the magnitude of k appearing. Please check this also. It's a very simple, same calculation, you will immediately see that this happens. Okay. So what this is now saying is that not only do I not care about where I place this chalk, but even at the particular location where I have placed it, I don't care about which direction this chalk is pointing. I can place it this way, this way, this way, this way, however I want. Direction does not matter if I only want to calculate statistics. It's called statistical isotropy. Okay. So these 2 conditions, the fact that you have independent Gaussians guarantees statistical homogeneity. And the requirement that the variance of each Gaussian only depends on the magnitude of the k vector guarantees statistical isotropy. So why is this interesting? Because our universe, the way we started by discussing is that let's consider a universe which is perfectly homogeneous and isotropy. Then we said, oh, actual universe is not homogeneous and isotropy. Okay, so we have to consider inhomogeneities and anisotropies. But in order to keep life simple, you impose another condition saying that, okay, it is inhomogeneous and anisotropic, but if I calculate statistics of the fluctuating quantities in this universe, those statistics will be homogeneous and isotropic. Okay, so the 2-point and n-point functions that I calculate will not depend on where you are doing the calculation and in which direction you are pointing to make the 2 points connect to each other. Okay, so you realize this statistical homogeneity and isotropy in this manner with a Gaussian random. Gaussian random field itself, of course, is slightly more generic than this because you could say that I want both statistical homogeneity and isotropy to be broken. So now you tell me, if I want to break statistical isotropy, how will I do it while keeping homogeneity intact? So if I want to generate a Gaussian random field which is statistically homogeneous, but it is not statistically isotropic, what should I change in this slide? Loudly? Yeah. What should I do to the variance?
It should not depend on
Correct. So this variance here should depend not only on the magnitude of k, but it should also pick up a dependence on the direction of k, and then I will break the isotropy. Okay, and how I choose to construct this function will decide what kind of anisotropy I am introducing. Okay, so for example, I can put in a dipole kind of effect here, and then I will see a dipole kind of anisotropy in my real space 2-point function. Okay, so you can ask this question. Suppose I want to make my CMB map, which looks statistically homogeneous and isotropic, but I want to convert it into that dipole map that I had shown you. Okay, what kind of P of K should I do? Right, so that is one question. And similarly, if I also want to break statistical homogeneity, what should I do? Excellent. Okay, so different K values should have their fluctuation amplitude that should depend on each other. So I should not have a Dirac delta here. I can think of instead a matrix which has off-diagonal elements in K and K prime. Right. So if I think of K as labeling one axis of the matrix and K prime as labeling the other axis, then what I want, so here what I'm getting is a diagonal, where when K is not equal to K prime, I have zeros. And only when K is equal to K prime, I have non-zeros. So now if I want to break homogeneity, I should allow for non-zero elements on the off-diagonal components. Okay, so that will be a random field in which I don't have homogeneity. It will also be a random field in which this statement will not be true. Right? Because now, when I have AK and BK, even if they are independent of each other at one value of K, they may need to depend on the values of AK and BK at some other value. Okay, so these are the kind of manipulations you have to do. And finally, to connect to the physics of inflation, so I said that the simplest models predict that the distribution should be close to a Gaussian. So they predict all of these things, that these AKs and BKs should be Gaussian distributed with some variance, and they should obey this Dirac delta kind of thing. But then these models go further and they predict for you the shape of this p zeta of k also. Okay, so that is the most interesting part about these inflationary models with quantum fluctuations. Not only do they predict that the CMB fluctuation should have a Gaussian looking form, they also predict the shape of the variance as a function of k. And that shape turns out to be something like this. So if you do a dimensional analysis, you will find that starting from here, if zeta is dimensionless, okay, and you work through all of these equations, you will realize that this p zeta should have dimensions of length cube. Okay, so it's a little bit of an exercise in dimensional analysis, but please check, this p zeta should have length cube. So when I take k cube times p zeta, I get a quantity which is dimensionless again. Okay, so this is called a dimensionless power spectrum. And these models typically predict that this dimensionless power should be some power law in k with some normalizing scale, and the power law index is some quantity which is very close to 0. Okay, so it is usually written as ns minus 1, and this ns minus 1 is a physical parameter in the inflation model which decides how small is the kinetic part of the inflaton field relative to the potential part. So this ns minus 1 really has a nice physical interpretation also in these models. So if you now, it's very interesting now, because suppose this zeta I can relate to an observable quantity, right, such as the CMB temperature fluctuations, and I go and I calculate the Fourier transform of the CMB temperature map, and I ask what does the variance of each mode look like as a function of the wave number of that mode. I can ask this question observationally now, and I can compare that answer with this quantity here. Okay, so as a function of wave number, if I can match it with a form that looks like this, then I can infer observationally the value of ns minus 1. And I can ask the question, how far away is ns minus 1 from 0? Right? And this is one of the key ways that one rules out classes of inflationary models today. So for example, ns minus 1 today has a value of something like minus 0.04 or 0.03, something like this. Okay, so it is actually in magnitude small compared to 1. So the universe that we see is consistent with the simple models of inflation, single field slow roll. And these models of inflation will give you a parameter which the observations are now constrained. Right? So this slow roll parameter is being constrained by measuring the shape of the primordial power. Okay. So this is very basic introduction to statistics of the initial conditions and how they might connect to observations. So in tomorrow's lecture, we will discuss the theory of how these perturbations are expected to evolve in the universe and what that implies for other observations. So there are some questions. So I'll just take the ones from Zoom. So there are no questions. So any questions here?
No. Experimentally, are there any candidates for inflaton?
No, because people consider that the Higgs could be an inflaton, but this Higgs inflation is a complicated problem of its own. There are many challenges to solve that. Apart from that, we don't know of any scalar fields apart from Higgs. So there are no experimental candidates. And then the other problem is that this Higgs, this inflaton field is supposed to do its job at 10 to the minus 42 seconds or something after the Big Bang, and then disappear for it. So it is difficult to see experimentally what you could do today which can realize the field itself. But what you can try to do is games like this, where you ask for predictions of a particular model on statistics of observables. So that is the game people usually play. These are statistics of correlations. There are other statistics of, for example, mostly it is coming from statistics of correlation. Not only in the temperature field, but also in the polarization. Or lake time structure formation will have some imprints of this. And so on. Yeah, I try to mention this.
मला म्हणे आम्ही कसं करणार ना सर्टिफिकेट जोपर्यंत भेटत नाही तोपर्यंत आम्ही कसं करणार मॅरिड अच्छा
Alright, so if there's nothing, we can stop and
मॅरिड म्हणून
Married म्हणून
ह्याचं बरोबर
Recording stopped.